So, torque. We had introduced torque. I'm going to give you some, we'll continue with discussing some of the properties associated with torque. But just to recap, we didn't do a whole lot. We'd started, but just to recap what we did say, as we defined what torque is mathematically, and we described what torque does. Well, actually, I guess I still have it here on the board. Let's just look at that then. Okay. Well, torque is torque is defined as resistant is defined as torque is it's proportional. So basically, this situation here, I have a door. So this is the side view of the door. Here's the handle where you would open the door like that, or push it in. Say it's a swinging door. And this is a top-down view. So the door is the red portion here. This is the hinge. So, a hinge with a D, or is it just DGE hinge? I think. Yeah. Uh, and this is the door. So I've applied a force to the door at an angle theta. But the force is, you don't have to necessarily pull on the door or push on it perpendicular to the door. So I've done it in such a way that there's an angle. There's an angle that my force, I'm kind of pushing it like that. And so I'm making an angle theta with what I'm calling the horizontal axis, the x-axis, which is the initial axis of the plane, the initial plane of the door. And so you can break up the force basically into two components. It's a little bit messy. So let me just come over here and do it again. So at least outline it here. So here's the hinge, here's the door. And basically, you could also say that if I'm applying the force at the edge of the door, at the handle, that's the position away from the perpendicular position away from the hinge that the force is applied. I might not be spelling that right. I don't know, but whatever. We got to keep going. Look it up later. So let's make this. Um, a force is applied at an angle. And the angle is measured relative to the line that extends essentially the position vector r. So again, this is the door, but it also represents the distance, at least the initial position of the door, represents the perpendicular distance from basically the position where the force is applied back to, well, essentially it would be what would be the axis, like the y-axis. If you like how I made it the z-axis. So like if I superimpose an axis on the problem, then I have I guess I made this the x-axis and the z-axis straight up. So the angle theta is measured relative to the axis here. So I could break up the force into two different components. A component that is perpendicular to the door. Remember, R represents the the length along the door, and a vector that is parallel to the door or anti-parallel. Because if I'm pushing on it on the door, then the force would be back along the direction toward the axis of rotation. And incidentally, the axis of rotation is here at the hinge. So those are all the kind of words that we use to define the, matching the physical quantities with the physics quantities or mathematical quantities. And so one of the biggest things we got out of this is that the parallel component of the force doesn't contribute to the torque. And it's more obvious that if you wanted to open a door and you went to, um, to the line that is parallel to the door and pulled on the hinge in that direction, you can pull all day long. You can pull it strong, pull it hard enough to pull the door off the hinges, but that's not going to make it rotate. And similarly, the perpendicular component, all of that force is going to rotation. And so when you think of a force that is at some angle, it's going to have both components, and it will only be the perpendicular component that is what we say, the language you use, contributes to the torque, that makes it rotate. The perpendicular component is F sine theta. The parallel component is F cosine theta. So that's why ultimately when we define the magnitude of the torque, given that by empirical observation, that's a double, by empirical analysis, these are the quantities that are proportional that increase or decrease the torque. The distance that that the force applies away from the axis of rotation, obviously the magnitude of the force, but also the sine of the angle, because the sine of the angle is telling you if the force is not completely perpendicular, it's telling you how much of, because remember, sine is just a number between 0 and 1. And so it's multiplying the total force and picking out only the contribution of that total force that is the perpendicular part, which, as we just said, contributes to the torque. So the torque is proportional to all of those things. And just a basic way that you make a formula empirically is that it's kind of like statistics, the same like when you do probabilities. And in fact, when you do probabilities, if there's multiple probabilities for something, then the total probability is not the sum, but the product of all the individual probabilities. When you're making a formula, that the most basic way, because this is not really theoretical. Theoretical is when you take several formulas, and then apply and apply the concepts associated with them to some physical situation, and then you get something. You get so yeah. This is more like a description, a definition. And all of the basic definitions in physics just come from us observing the universe. And basic definitions like, what is gravity? The actual formula. What is electric field? Coulomb, or what is force? Sorry, not field, but what is the Coulomb force? What is the gravitational force? In this case, what is the torque? And so that becomes the definite. That's why we call it a definition as opposed to like it's not a theory. So it turns out that that happens to be associated with some sort of mathematical concept, that whenever you have the magnitude of a vector quantity times the magnitude of a vector quantity times the sine of the angle between them, it turns out that that happens to be a certain type of product called a cross product. And that's a mathematical thing. But the mathematical concept of cross product has its own properties. But sometimes in physics, when it turns out that a physical quantity, which is different from the from the cross product, excuse me, when a physical quantity is defined by a mathematical quantity, then the physical quantity has its own properties, of which we're discussing, but it also takes all of the properties of that mathematical concept. So, yeah. And so what I've described to you here is kind of a combination of both, but it's showing you that when you take a cross product, you're basically picking out the part of in terms of the magnitude of the torque that is, um, that contributes to whatever that quantity you're describing. In this case, torque, and of course, the torque causes something to rotate. So, we said a lot of things, but basically, a force gives rise to linear acceleration. As it turns out, a torque gives rise to angular acceleration, because if this thing is not rotating and then it starts rotating, that means that initially it had a zero angular velocity, then it has some non-zero angular velocity. That means the angular velocity changed, which means that it also had an angular acceleration. So, and we've already defined all those quantities last chapter, but that's basically, you know, basically what a torque is. It is the thing that causes any kind of rotation that you see anywhere. Well, excuse me. It is the thing that causes a change in rotation. Because just like with linear motion, once something starts to rotate, first law applies, it'll just continue to rotate unless another torque comes along and either increases that rotation or decreases that rotation. Just like in motion, you can start something falling or start something moving, and if you're out in space, it just continues to move forever at that constant speed unless you then apply another force to it to change the direction or speed it up or slow it down. All of that still applies for rotation. Yeah, so torque is the thing that causes rotation or change in rotation. Yeah. Okay. Oh yeah, the direction. So that's probably where I think we did go over the right hand rule. Didn't I? Maybe I didn't. Did I not? Oh, yeah. So we have to figure out that's what's a little bit different as well, is that the direction of torque is going to be perpendicular to both, unlike linear motion, when the direction of the acceleration and the direction of the net force that causes that acceleration is always in the same direction. Um, yeah. So if something is speeding up, the net force will be in the direction of that acceleration. If something is slowing down, even if they have several forces on it, they will all add up together such that the net force is opposite direction of motion, but parallel to the direction of acceleration. Because when you're slowing down, right? So when I'm speeding up, acceleration, velocity, and net force are all in the same direction. But when I'm moving forward and I start to slow down, my acceleration and my net force are opposite direction I'm moving. So my point is that even though acceleration and net force can change, can be parallel or anti-parallel to velocity, for linear motion, they are always parallel to themselves. The net force is always parallel to the acceleration for linear motion. But with rotational motion, as it turns out, the net force and the acceleration are always perpendicular, defined as perpendicular to the plane of motion. And one very easy way to illustrate that is, let's say that I take this ruler and I start to spin it around like that. Well, it's rotating in the plane of the board. But if I describe the plane, let's use this axis right here that I've used. So up is Z, to the right is X, which means Y must be coming out of the board. So the plane of the rotation is in the X and is in the Z and XZ plane. So it doesn't make sense that I would use either X or Z or any combination to describe the direction of, let's say that there's a dot here and the dot is moving around in circles, mapping out a circle, as opposed to thinking about the whole thing. It might be easier to think about a dot moving around a circle. And I could even illustrate it here. Let's say that I don't want to mess that up, so I'm just going to do it here. That's a nice circle, as you. So we have a circle and the rotation is clockwise. And so at any point, the tangential speed is going to be V. And remember, this is the Z-axis and this is the X-axis. So at that point, as I move around, it has infinite direction, right? 360 degrees. So it doesn't make sense that I would use Z or X to describe the position or any combination, of that position or of that rotation. And so the angular velocity, the angular position, the angular velocity, the angular acceleration, what they do have in common is that all of the motion is in the plane of the board. And if I have a line that is perpendicular to that plane, the direction of that line always establishes the direction of the plane, and therefore establishes the plane within which the object is rotating. Let me show you what I mean a different way. I had a little. This is here somewhere. Well, I just take a piece of paper. Assume this piece of paper was like a circular pattern here, or just whatever. The thing is moving in that circle. So if I take this and I have an axis that's perpendicular to that plane, I can move it all the way through space, and this is definitely pointing in a direction because it is a direction, like it's the y-axis. So if I move my axis around, the y-axis is always going to be pointing parallel to that line. But once I know the direction of that y-axis, I also know the direction of the plane, even if it's changing. So then I know the direction of where the plane is or how it's oriented with my relative to my y-axis, namely 90 degrees. And so then I understand something about the rotation of the relative rotation of the mass. So for that reason, the coordinate that would define all of those quantities, the Cartesian coordinate that defines all of those quantities, namely theta, angular velocity, angular acceleration, is actually, in this case, would be the y-axis. Always the axis that is perpendicular to the plane in which the rotation happens. So if I'm moving around, my theta, so I'm at this position at one point, this position at another point. So this is my theta, my angular displacement. And each of this would be like theta initial, and this would be like theta final. So those angles, they would be defined as theta j, because it's in the j direction. The change in theta also, omega, the change in theta with respect to time, which is the angular velocity, is also, because I chose counterclockwise, and it's actually negative. Technically, it would be the negative y-axis, and I'll talk about that in a minute. That's associated with the right-hand rule. But the axis, the point I'm just trying to make is that the axis is the y-axis. And the same thing if the angular velocity changes, namely angular acceleration, it's either going to be positive or negative y-axis. Now, so now in your book, they generally set up the situation so that the object is rotating in the xy plane, so that the z-axis is the coordinate direction that is perpendicular to the plane of rotation. And they just make all the problems like that. So don't let that confuse you or trip you up. And most books actually do that. So they even, to emphasize the point, when you have a standard, an axis where, what's kind of like this, where z is up, but usually, actually, I kind of messed this up in it because it is actually the positive y direction, but positive y is into the board when it's like that. So I said it was out of the board, but it's not. X, Y, Z. Yeah, positive Z would be into the board. So looking down, I don't know, it's kind of, let's make this Y, because that's standard. You'd have X coming out, Y going in. So X, Y, Z is up. Yeah. So in that case, if we're looking straight down from this point of view, yeah, that's just, I don't know, whatever. So yeah, let's just talk about the right-hand rule right now. Let's go ahead and make this, so if we're doing kind of axis that they would do in the book, Z is going to be coming out of the board. And if that's the case, X would be, so looking top down on this axis, we would get something like, this. So X, Y is here, X is here, Y is here, and Z is out of the board. So X, Y, Z. So if I'm rotating in the counterclockwise direction, then for that scenario, the direction of the rotation would be in the negative z-axis. And we accomplish that by applying something called the right-hand rule. There's various ways of applying the right-hand rule, but one of them is a method that I call curl point, where it's a more intuitive method of the right-hand rule. There's 3 different ones that I teach, and this is one of them. Probably the easiest is curl point. So you curl your fingers in the direction of rotation, make a fist, and then your thumb points in the direction that defines that rotation. So curl fingers along the orientation of rotation. So curl fingers with rotation. Efficient language. And then point thumb we'll say parallel to direction. Curl point. So any rotation that applies to anything that you see rotating. If you take your right hand, let's say you walk up and there's a Ferris wheel, and the Ferris wheel is spinning. Let's say if you're looking at it spinning in the counterclockwise direction. Curl your fingers in the direction of the rotation. Your thumb points back toward you. That would define all of the quantities, the angular displacement, the angular velocity. Well, if it's moving at a constant rate, it would have a 0 angular acceleration. And you have to be a little bit careful for the acceleration. If the thing is speeding up, then you're fine, curl point. If it's slowing down, you have to curl point and then flip, because slowing down means it's negative acceleration. So just keep that in mind. But yeah, curl point method is that's more intuitive because it's following actually what's happening. And yeah. But there's another right-hand rule which applies to this formula, which is not intuitive. It's associated with a mathematical form of cross product. And again, as I told you, it's not specific to torque. It just so happens that because torque is a cross product, then the right-hand rule that applies to cross products also applies to this one. And different ways of teaching it. It doesn't really have a name. They don't have a name, but they usually use thumb, index, and middle finger. I do it a different way. I follow this method that I'm using with a kind of an acronym, and I call it run wrap point. And I'll explain that to you here in a second, and then we'll look at some examples. But before I do that, I got to take a quick 5-minute break. But let me write this down. Right-hand rule again, I'm going to abbreviate right-hand rule. And this one is run, wrap, point. And also, usually I do put a flip in this if it's negative. So if you have it, well, you won't have to flip here because you only flip if you put in a negative sign. But yeah, so let me take a quick break. We'll come back. I'll describe the run wrap point with respect to generically with respect to any kind of vectors, and then we'll look at torque where I'm opening a door or something like that, and we'll with R and F vectors, and we're practicing. I'll be right back. Yeah, whatever. But run wrap point. Okay. Whenever you have now, this is covered in like calculus. I think the dot and cross product are probably in calculus 3. I think in the second or third chapter of this book, second chapter, they also probably went over this. So you probably see it there, but their method is going to be a little bit different than what I teach here. So if you have a vector like, well, let's just do an example of specific to our cases. So I'm going to go ahead and write all these up, and then we'll go through them. I'll use the first one to illustrate the point. So examples. So in all of these examples, basically give the direction of the torque, excuse me. So if I have an axis of rotation here, so that's the AOR, and then I have a position vector pointing like that, so R, and then F is pointing straight down, and so these are in the plane of the board. So the thing is, apply the right-hand rule, run rat point, to figure out the direction of the torque. So I'll do it. I'm gonna just write all these down so we can go through them, and then I'll. And also, you can practice because we're gonna run out of time at home, and then you can ask me about them if you need to. Just to help guide your eye, I'm gonna have a different color for the vectors. So here, I'm going to make the force, and you can draw them different ways. I could draw them head to head, like I'm doing here, or I could draw them head to tail, like I did here, or tail to tail. It doesn't matter because you can always project the vectors to the thing that you like the best. For me, I like the head to tail method the best whenever I'm doing the right hand, but it doesn't matter. So I just want to get you used to all the different variations and versions, and so I'm writing them differently. So 3. Um, and then 3 is yeah, there's 3. So R, just in the interest of time, because it's going to take me longer. I'm just going to do it like this with same color so I can write more in the 10 minutes I have left. And then F here, R like that. And so here, R is into the board, and F is straight out like that. And 6. So now R is down, straight down, and F is out of the board. Then 7 over here, F into the board, and R. R is pointing like that. Yeah, I'm keep forgetting to put the AOR on all these. So obviously with these two, the AOR is going to be where the cross is or where the dot is. And so in the case, in your, yeah, so like in this case, this would be a situation where you're looking. So let's say that this vector is R. No, so this is vector is R, so the cap is the point. It's pointing in like that, but the force is like this. So when you're looking down, all you see are is the tail of the vector, but it doesn't mean that. Well, yeah, I guess if the force is actually at the axis of rotation, you're not going to get any rotation at all. So I guess the assumption is that it's not. So it would have to be over here. It has to be anywhere between the axis of rotation and the tip of R. So that if that's the case, you would get a rotation. If it's at the axis of rotation, then that's kind of the trivial answer. Because you don't get, like we pointed out the other day, you don't get any rotation if you press a force on the hinge. Right, you have to come a distance away from the hinge, and any distance away gives you some kind of torque. The farther you are away, the more torque you have, as we said earlier. So make that assumption about these, that the force of the R, they're not at the origin, they're someplace. R is a distance, F is being applied a distance away from the axis of rotation, but visually you wouldn't be able to see that because of the orientation of the view. Okay, so here we have AR would be there. So where there's a dot, that represents the axis of rotation. Okay. And then finally 8, we have this guy. This is R, and F is going to be into the board. And then And F is back up like that. And 10. Sorry, F is pointing away. Yeah. And R is out of the board. Okay, so plenty of examples. Let's come back here. 10 minutes. Plenty of time. So, and I don't have room to write here, so I'm going to come over here. We are going to run our hands like an arrow. Run out. And when I say hand, I mean whole arm. So thing about doing the right, and the reason I do it like this is much more cumbersome than what they're going to teach you. And most people teach it, just to be fair, the way they do it in the book, with your pointing your thumb along the direction of the first vector in the cross product, your middle finger then parallel to the second vector, and then your thumb points in the direction of the resulting vector, in this case torque. A couple of reasons I don't like that. One, because of my physiology, it's kind of hard. It makes me feel funny whenever I do that with my stretching my hand in that way. But another reason that came about ultimately because of when I started teaching is that, like it's kind of akin to that idea that the more senses that you use whenever you're learning something, the more efficient the learning process. Now it's true you're using physicality when you're doing all that, but it's kind of limited. You're kind of like in your head trying to match that thing to the physical, imagining the physical situation. I found that if you actually go another step further and physically try to mimic, match your body with the scenario more specifically, it actually helps the learning process better. So the first process in run wrap point is to run your arm like an arrow in the direction of the first vector. When I say arm, I mean from your elbow to the tip of your fingers. And when you do that, it has to be straight, rigid, like an arrow. So you can't have bends in your arm or anything like that. It has to be conscious about all of that. So run your arm like an arrow parallel to the first vector. Just as parallel to R in this case. So wherever R is, you have to physically get up and do it. Here, R is like that, and like it's kind of awkward, right? So you don't want to do this. That's what I'm trying to say. You could fudge it if you know what you're doing, but if you know what you're doing, you could do it in your head. So if you have to actually use a physical right hand rule, it means that there's something about it that you're unfamiliar with. So don't slack. Take your arm, make it like an arrow. However you have to contort it, your body, make sure you're doing that so that your arm is parallel to that vector wherever the space you drew it. Physically doing all of that makes you somehow subconsciously or maybe consciously think about the concept. Trust me, I've been teaching this particular thing for probably 20 years. And over time, I can see that when students actually get up and do it and physically walk around, however they're doing it, even if it's on your paper, like get up and make it parallel, somehow they learn it quicker. All right. So run your arm like a arrow parallel to R. Now, the second step is that you have to curl your fingers or bend your fingers, curl your fingers, just this part, not your hand, just your fingers, so that your fingers are parallel to F. So I'm going to use the term bend because I use curl whenever you're, wrapping. Well, I guess I use wrap. Sorry. So wrap your fingers, and I use curl whenever you're kind of moving around. But wrap means to just, bend your fingers. And when you do that, the rest of your arm stays parallel to R. So wrap your fingers, uh, wrap fingers parallel to F. And I'll say keeping arm parallel to R. Now, if you're in an odd configuration, you're going to have to again move around, like because your fingers can only bend in one orientation relative to your hand. That's not a bend, right? You're not bending. You can't bend your hand back opposite the manner in which the joint swivels. So your hand can only bend or wrap like that, which means that if F is down, you have to physically rotate your arm so that it's in that configuration. That if you just happen to do a problem or start with where the orientation of your body is such that you don't have to do much movement, fine. But inevitably, if you do a lot of configurations, that won't happen. So physically, what I'm suggesting that you do, at least when you're first learning, is physically get up and do all those movements. So run, arm like an arrow, wrap your fingers parallel to F. That's not parallel to F. That's not parallel to F. That is parallel to F. And physically, you can see that it is. Forearm is parallel to R, F is parallel to F. When you have that configuration, make a fist and point your thumb without moving anything else. So, point, thumb, parallel to basically the answer that you want. So it's giving you the direction that the torque will be for that situation. So in this case, run, wrap, point. So for this case, the torque would be into the board. So torque, and then the answer, to give the answer, you would give the answer basically with those, remember a crosshatch is in and a dot is out. So the answer would be that torque is into the board. And you can see from this that the rotation is perpendicular to that direction, the plane of rotation. Because again, if I have something like this, right, it's pivoted there and I apply force down, it's going to rotate in the clockwise direction, right? Initially, anyway, it does. It wants to rotate down. So, the direction of the force would have to change for it to rotate in a circle. But in that instant, its velocity is zero. The force applies it applies down, and it starts to rotate in the counterclockwise direction so that its angular velocity is increasing. So that during that change, it has an angular velocity, a change in angular velocity, and an angular acceleration. And all of those quantities would be defined as into the board, which would, I guess, in our case, be if the negative z direction, keeping in with the choice of orientation that I set up in the last demonstration. Yeah. And so that's it. That's the right-hand rule with the run, wrap, point method. So let's do this real quick. So run your hands like an arrow in the direction of R. So I'm down like that. But now F is coming back in this direction. So I have to, so you see, this is a situation where my orientation of my physical body just didn't happen to be natural to the problem that I'm solving. So I got to do a little bit of work, right? I've got to turn my hand. Now, there's a couple ways. You say, that's what I'm saying. You have to think about it. If you're unfamiliar with it, that's where you would have to think. It's a little bit confusing if you're not. But F is back in that direction, and I've got to get these fingers going back in that direction without moving this, part of my arm from my elbow to my wrist. So the only way that I can do that is if I swivel my wrist so that I can now bend my arms back, my hand back in that direction. So you can see now that my fingers, are definitely parallel to F, and my forearm is still parallel to R. Okay, then make a fist and point. Torque is into the board. Run, wrap, point. So into the board. And sometimes I always ask also what would be the orientation of rotation for that torque. And since I got you here, I'll go ahead and teach you the third right-hand rule. So here we know R and F, and so we're using R and F and the definition of torque to figure out the direction of torque. But what if I just told you the torque is into the board? How would you know the direction in which it rotates? Well, it's the opposite of curl point. It's point curl. Now you know the answer and you want to know what resulted in that answer. So curl point method is you take your thumb with a fist, point your thumb in the direction of the torque, and your fingers will curl around in the orientation that torque would cause, a rotation of that torque. So that torque, again, it's give you the answer that we just determined, but it's clockwise. So the curl point method, so this is run wrap point, right hand rule, and the curl point method of the right hand rule is the point curl. So there's curl point, which is the first one. This is run wrap point, and this is point curl. Point curl method is to point your thumb and wrap your fingers. So you're not going to find these in a book anywhere. This is my if I were writing a book, this is what I would do. So if you go ask anybody, what is the point curl method of right hand rule? They're like, what? I don't know what you're talking about. So point thumb parallel to the torque and wrap fingers. I don't really want to say parallel because circular motion, you're not parallel to it. You're only parallel to a tangent of it. So the language that I use is wrap fingers. The fingers will wrap in the orientation of the motion, in the orientation of the rotation. Wrap fingers along orientation of motion. And of course, the implication is that the motion is rotational motion. I don't want to say orientation of rotation. Maybe I should. It has a ring to it. Wrap fingers along orientation of rotation. Yeah, maybe. The ring. So I'll use that language. Orientation of rotation. But yeah. So in all of these, you could use the curl point method to figure out the torque and then verify the orientation of rotation by using the point curl method. And I'm sure we've gone over. Yeah, I've gone 3 minutes. So let me do a couple more for you. Be careful on things like this, right? Because here you might be tempted to wrap your fingers in the direction of R and then, curl your fingers back, whatever. And then, I don't know, you probably do something like that, but that's wrong because you have to remember the definition as well. The definition is the magnitude of R, the magnitude of F, the magnitude of the sine of the angle between them. Well, what's the angle between these two things? It's 180 degrees. And the sine of 180 degrees is 0. So the torque here is 0. Now, you knew that. I know you knew that, but many of you who knew that answer might have gotten it wrong. That is the difference between left and right brain, analytical versus intuitive, which is why I like to use those words in class. When I describe, and it depends on the perspective that it gives you, whether that becomes obvious or not. It also depends on your background, like what your sensibility is, because what's obvious for someone might not be obvious for another person. But whenever I presented this, as a door, and I was saying you push on the door or pull on the door, and it's not going to give you a rotation, most of you probably say, well, okay, duh. Yeah, of course. Why? Because that's intuitive for everybody because we all use doors. Again, remember the 4 themes of the course: perspective, specificity, symmetry, and technique. This is a situation where just presenting something that is completely obvious from a point of view and a perspective that is not so obvious because people aren't used to it, you would completely miss it. And this is an example of that, particularly if I get you thinking in one way by asking about from, various points of view where there is an angle and then throw this on. It's just like your mind has a inertia to it, using a physics term, that it wants to kind of keep doing the same thing. But that's just the nature of physics. You have to be careful, right? There's a couple of different definitions that apply. One is analytical, associated with the definition of of torque and the cross product. The curl point method and the point curl method are completely intuitive. There's no equation associated with those. So intuitive, they're just based on the experience and the empirical experience about how those things work. Now, I know I said a lot there and I didn't need to say all that, but I'm also trying to point out to you why perspective, those things are themes, because this kind of thing pops up in physics like out of the blue before you know it. And so I just want to point it out to you. So that's zero. And those rules don't apply because the cross product trumps that. And if I were to put them parallel to one another, like this would be the same thing because the angle would be zero. So it's akin to pushing and pulling on the door. So we're back to this one. So I'll do that one, then I'll let you do the rest as a class exercise at home. And you can ask me about them specifically on Monday if you have difficulty, but we'll do one more. So run wrap point. Clearly there's an angle. Oh, one other thing let me point out to you. One other thing I want to point out. And that's also specific to whenever you're trying to calculate the magnitude and you have a non-zero or 180-degree angle. You got to figure out what is the angle. And it's not so obvious when I draw a vector like that. The angle between two vectors is always when you project them head to head or you project them tail to tail. In this case, but what about if it's head to tail? Or you can't, it's not so obvious. Well, like this guy, for example, it's head to tail. And so is this the vector, the angle, or is it the obtuse? That's the angle that defines the cross product. Well, in this case, it's the obtuse, which I don't think is obvious. It wasn't obvious to me when I was first learning it. But one way you can always get it is you project out R, just like I did when I did the door. Project out the R vector, and that's the same thing as projecting F back to the origin where they're head to head, or tail to tail. So like if I projected F back, kind of like that, then it would be obvious from that point of view that that's the angle between them, which is the obtuse angle from this point of view. But the equivalent is projecting R out and then getting it. So just a note about that. Little subtle things like that that come up only when you're doing various problems, and they don't come up whenever you're defining something or whatever, or presenting it initially. So I'll do this, I'll let you go. So technically the angle between these guys is actually it's actually this angle. And if I projected this out and then projected this out, you see that that's the same angle. Alternate interior angles. But to do the right hand rule, so I'm going to move over and mimic what I taught you. Move your body. So run your arm like an arrow parallel to R. F obviously points down, or points, in this way. So both, again, my forearm is parallel to R. Simultaneously, my fingers are parallel to F. Make a fist and point. The torque is out of the board. Torque is out of the board. So there you go. Out of the board is represented with a circle and a dot. And the angle of rotation, or the orientation of rotation, is going to be counterclockwise. So you might put that in as well. So like here it'll be like that, and you might represent that as omega. And so omega would be out. And again, be careful. That doesn't mean that omega is defined as out of the board, like with the torque, and here into the board with the torque, but you still give the orientation of rotation associated with omega. Here, same thing. Omega would be kind of around like that.